In this lecture, we're going to discuss synchronization tools. We'll break it down as follows. The background of them, critical section problem. We'll first look at Peterson's solution. Then we'll look at some synchronization hardware approaches, mutex locks, semaphores, and monitors. Now, these not only come up in operating system design, but some of these come up in actually application programming where you're doing multi-threaded or multi-process development. So, processes can execute concurrently, and they can be interrupted at any time, partially completing their execution. Concurrent access to shared data may result in data inconsistency. So, the example is, for example, that we grab the value 3 from a memory location, then our process gets hijacked. The other process updates that to 5. And then we go back to the first process where now the values don't match. And that can cause all sorts of nightmarish problems debugging. Maintaining data consistency requires mechanisms to ensure the orderly execution of cooperating processes. We have to synchronize shared regions. So, suppose we wanted to provide a solution to the consumer-producer problem that fills all the buffers. We can do so by having an integer counter that keeps track of the number of full buffers. Initially, counter is set to 0. It's incremented by the producer after it produces a new buffer, and is decremented by the consumer after it consumes a buffer. So here would be the code, like we saw before. While true, produce an item. While counter equals buffer size, do nothing, basically wait for the buffer size to change. Then buffer in equals the next produced item, and then we update in and counter plus plus, just like before. Similarly, we do the same thing, or the opposite side for the consumer. But here's where things get interesting. Counter plus plus could be implemented as register 1 equals counter, register 1 equals register 1 plus 1, counter equals register 1. Similarly, counter minus minus could be implemented using the same strategy. But if we interleave with count equals 5, so state 0 producer executes register 1 equals counter, so register 1 equals 5. S1 producer executes register 1 equals register 1 plus 1, so register 1 equals 6. S2, the consumer executes register 2 equals counter. Okay, so register 2 equals 5. Consumers executes register 2 equals 4. Producer execute counter equals register 1. And then it executes counter equals register 2. So basically, we've now got inconsistent results. So, in general, this is called the critical section problem. Basically, we consider a set of n processes, P0 through Pn-1. Each process has a critical segment of code. The process may be changing common variables, updating tables, running files, etc., anything that's shared. So what we do is we take the solution and have one process in critical section, no others can get in that section. The critical section problem is to design a protocol to solve this. Each process must ask permission to enter the critical section in the entry section. It may follow a critical section with an exit section and then a remainder section. Let's look at an image here. We've got our entry section, our critical section, and an exit section, and whatever comes after it. Okay, so algorithm for process P is while turn equals J, one approach, critical section, else we set turn equals to J and do the reminder section. So basically, we wait until turn changes, we do our critical section, and then reset it. There are flaws in this that we will come to. So there are a couple solutions. Well, there's some concepts in critical section problem that must be observed. Mutual exclusion. If process PI is executing in its critical section, nobody else can get in there. Progress. If no progress is executing in its critical section, no process is executing in its critical section and there exists some processes that wish to enter the critical section, then the selection of the processes that will enter the critical section next cannot be postponed indefinitely, basically avoiding what's called deadlock. Bounded waiting. A bound must exist on the number of times that other processes are allowed to enter the critical sections after a process has made a request to enter its critical section and before that request is granted. So basically, if each process executes at non-barrier speed, no assumption concerning the relative speed of the end processes can be made. This is also to protect lockout. The two approaches depend on if the kernel is preemptive or non-preemptive. A preemptive kernel allows preemption of process when running in kernel mode. Non-preemptive runs until it exits kernel mode, blocks, or voluntarily yields the CPU. Essentially free of race conditions in kernel mode. So the first approach, Peterson's solution, is a good algorithm restriction of solving the problem. It is a two-process solution. So we assume that the load and store machine language instructions are atomic. They can't be divided. So the two processes share two variables, turn and flag. The variable turn indicates whose turn it is to enter the section. The flag array is used to indicate if a process is ready to enter the section. So flag sub I equals true implies that process P of I is ready to enter the section. So here we have a loop. Flag I equals true, meaning we're willing to enter process I. We're ready to enter process A. Turn equals J. Where flag sub J and turn equals J. So basically, if the turn is ready and the flag says we want to get in, we do our critical section. Then we set the flag to false and do our remainder section. So Peterson's solution is provable that the three requirements are met. Mutual exclusion is observed. PI enters CS only if flag sub J equals false or turn equals I. Progress requirement satisfied, and the bound waiting requirement is met. So now we're going to come to the concept of synchronization hardware. Many systems provide hardware support for implementing critical sections code. All solutions below are based on the idea of protecting a critical region via locks. For uniprocessors, we could disable interrupts. Currently running code would execute without preemption. Generally, though, this is too inefficient on multiprocessor systems. It's not broadly scalable. Modern machine provides special atomic hardware instructions. And by atomic, again, we mean non-interruptible. Either they test memory word and set values or swap contents of two memory words. So here what we do is we'd acquire a lock, do our critical section, and release a lock, and then a remainder section. So basically a test and set instruction could be implemented thinking of it like this. We send in a target. We set the value of RV to target. We set the target to true, and then we return the original value. And we set the value and set it to true. So here's a solution using test and set. A shared Boolean variable lock is initialized to false. Solution, do while test and set lock. So while it's locked, do nothing. When it is free, we then do our critical section. We then set our lock equal to false. And then we continue on our merry way. Now there's also compare and swap. Okay, it takes a value expected and a new value. And we assign it to temp. If value equals the expected value, then value equals new value, and we turn temp. Again, this is atomic. Returns the original value of the pass parameter and sets the variable value to value the pass parameter new value, but only if it's the expected value. It only takes place under the specific condition. So the shared lock in an integer lock is initialized to 0. And you would say, while we're waiting for the lock to become available by comparing and swapping it when necessary, we do nothing. And then we do our critical section and then reset the lock. So here's bounded waiting mutual execution with test and set. So waiting of I equals true. We set our key equals to true. While waiting and key equals test and set. So we keep doing this until we get back a true result and we're still waiting. Then we set our waiting to false because we're no longer waiting. We get into our critical section. We do some stuff. And then when we're done, we reset our lock and go home. So the previous solutions are complicated and generally not accessible to application programmers. OS designers build software tools to solve critical section problems. The simplest is a mutex lock. It protects a critical section by first acquiring a lock and then release the lock. You almost call lock and unlock. And it's a Boolean variable that indicates if the lock is available or not. Calls to acquire and release must be atomic, and these can be implemented via hardware atomic instructions. The solution requires busy waiting, though. That's a problem. So this could be called a spin lock, as in it constantly is being checked and spun until you're able to get into it. But it's the same basic concept. Acquire while not available, wait. Otherwise, available false. Release sets available to true. Okay, so we acquire our lock, and we spin and pin and spin until it's available. Then when we hit our critical section, notice available is false. And then at the end, when it hit release, we re-enable that critical section for others to use. A semaphore is a synchronization tool that provides a more sophisticated way than mutex locks for synchronization. S is an integer variable in a semaphore. It can only be accessed via two indivisible and atomic operations, wait and signal. When this was originally designed, they were called P and V. Don't ask me why. I don't know. The definition of the wait operation is, while S, an integer, is less than 0, we busy wait, and every time it gets to 0 or more, we decrement it. And basically it unlocks things. Signal, on the other hand, increases S, so it can force us to an unlock point. So there are two types that we pretty much deal with. Counting semaphores. Integer value can range over an unrestricted domain. Then there's binary semaphores. It's basically the same as a mutex lock. And we can solve various synchronization problems. Consider P1 and 2 that require S1 to happen before S2. We can create a semaphore sync initialized to 0. So first we have a semaphore S1. We have our section S1. And then we signal to sync that we're available, that the sync is ready. On the other hand, we wait for the sync to become available, then we do S2. You can also implement a counting semaphore S as a binary semaphore. It must guarantee that no two processes can execute the wait and signal on the same semaphore. The implementation becomes critical section problem where the wait and signal code are placed in the critical section. We can now end up with busy waiting in the critical section, but the implementation code is short and a little busy waiting is okay if the critical section isn't used much. However, usually applications may spend a lot of time in the critical sections, and so this isn't a great solution. There is a way to implement this with no busy waiting. So we associate a queue called the waiting queue. And each entry in a waiting queue has two items, the value and the pointer to the next record in the list. So there's two operations. Block, place the process invoking the operation on the appropriate waiting queue, and wake up, which removes one of the processes in the waiting queue and places it in the ready queue. So we define a structure semaphore, which has a value and the next pointer in the process. So waiting basically decrements the value. And if the value is less than 0, we add this to the semaphores list, and then we block. Signal, on the other end, increments that value. And if we're in our appropriate range, we then remove a process from the list and we wake it up. Okay. Let's talk about deadlock and starvation. 2 or more processes are waiting indefinitely for an event that can be caused by only one of the waiting processes. So let S and Q be 2 semaphores initialized to 1. So on process 0, we wait for S, and on process Q, we wait for Q. On process 0, we wait for Q, and then we wait for S. The problem is that S is waiting on, process 1 is waiting on Q, which is waiting on S, and process 2 is waiting on S, which is waiting on Q. So basically, you could get stuck with things in the semaphore queue pretty much permanently. So the way this is often dealt with is by doing what's called priority inversion, and it basically has a priority inheritance protocol. Basically, priorities get increased or decreased as necessary to break that. So here's some incorrect uses of semaphores: a signal followed by a wait, or a wait followed by another wait, or omitting of one or the other. And this can cause deadlock and starvation, and those are no fun. Now we come to monitors. A monitor is a high-level abstraction that provides a convenient and effective mechanism for process synchronization. It's an abstract data type, and internal variables are only accessed by code within the procedure. Only one process may be active within the monitor at a time. Usually this is done via programming languages. But it's not powerful enough to model some synchronization schemes. But here's how it would work. You'd have a programming language construct called monitor with a name and various procedures within it. And essentially, they would be only allowed in via queue. Okay, the other thing is condition variables. 2 operations are allowed in a condition variable: x.wait, a process that invokes the operation is suspended, and x.signal, resumes one of the processes that invoked x.wait. If no x.wait on the variable, then it has no effect. So we can use that alongside with condition variables, and that will give us a more powerful solution. So consider some variable choices. If process P invokes x.signal and Q is suspended in x.wait, what should happen next? Both Q and P can't execute in parallel. If Q is resumed, then P must wait. So we could signal and wait. P waits until Q either leaves the monitor or it waits for another condition. Signal and continue. That's Q waits until P either leaves the monitor or it waits for another condition. Both have pros and cons. Language implementer can decide, although you don't see them all that often. Concurrent Pascal implemented it as a compromise. P executing signal immediately leaves the monitor and Q is resumed. They are implemented in other languages, including Mesa and C# and Java, but they're not done quite as, they're there, but they're really not used all that much. You can use semaphores to implement a monitor. And so basically, you wait for a mutex. If the next count is greater than 0, then we signal the next. Otherwise, we signal the mutex. So that way it'll release. For each conditional variable, we have x.wait can be implemented as counting for that particular variable. And if it's greater than 0, we signal. Otherwise, we signal the monitor. Otherwise, we signal the mutex. I'm sorry, the conditional variable. Otherwise, we signal the mutex. And then we wait for the semaphore to let us through. So, and here's the implementation of x.signal. And next count is incremented, and then we do a signal, then a wait on we signal the semaphore to say something else can run, and then we say wait on this particular one, moving to the next in the list. This is rather complicated, and the nice thing is about it is that there are features within most languages these days to make this much easier. So if several processes are queued on a condition and X signal is executed, what should be resumed? First come, first served often fails. So we usually have a condition wait construct of the form wait C, where C is a priority. Processes with the lowest priority number are scheduled next because they're the highest priority. We can allocate a single resource among competing processes using priority numbers that specify the maximum time a process plans to use the resource. And R would be an instance of a resource allocator. So here's a monitor to allocate a single resource. We have a condition X, we have acquire, which says if it's already busy, then we wait on it, and then when we're done, we say busy is true. We go into our critical region, and then with release, we just set the busy to false, and then signal that we're done to release any waits. So that's the overview of synchronization methods, and I know they're confusing, but the reality is the best way to deal with them is to play with them, is to look up whatever language you're using and its libraries for semaphores and mutexes and give it a try.